Up until this point in class, when we've chosen to represent the forces acting on a particular object, we've just made qualitative representations showing the size and direction of forces acting on that object. We've also answered questions like what direction is the sum of the forces in on that object, whether it's increasing, decreasing speed, or moving at a constant velocity. In this video, we're going to learn how to figure out how big those forces are. Not just whether forces are balanced, but exactly how big those forces are as measured in newtons. And we're going to learn how to do that whether forces are just in the x or y direction, or if they're forces at an angle with an x and a y component, or even for situations where there's an object on a ramp or an incline, where we already talked about having to rotate our coordinate system where the x direction is parallel to the surface and the y direction is perpendicular to the surface. Let's first take a look at a simple situation with a person of mass m standing on the earth. Let's make a symbolic force diagram and a quantitative force diagram. Well, if somebody's standing on the earth, we know the earth is attracting them with gravitational force and the earth is pushing up with a normal force. If the person is at rest, we know those two forces have to be the same size. But let's go beyond that. Let's first come up with a symbolic solution or a symbolic answer for how big the force of gravity is and how big the normal force is. In our Force of the Earth lab, we learn the relationship between the force of gravity on an object and its mass and the gravitational field strength of the planet that the object is on. This is what it looked like in our lab. We found out that the force of gravity on any object was equal to the object's mass times the gravitational field strength of the planet. So the symbolic answer for the size of the gravitational force is just m times g, the mass of the person, in this case, times the gravitational field strength of the earth. And since the force of gravity is the same size as the normal force because the person is at rest, that means the symbolic answer for how big the normal force is also m times g. That's not true in all cases. That's just true in this case that the normal force is equal to mg because it's equal to the force of gravity. Now, if we wanted to find out quantitatively how big those forces are in newtons, then we could use our symbolic solution. So let's say the person has a mass of 80 kilograms. How big is the gravitational force and how big is the normal force? Well, let's just use our gravitational force equation. The gravitational force, or the weight of the person, is equal to their mass, 80 kilograms, times the gravitational field strength of the Earth, which is the amount of force that the Earth exerts on every kilogram of mass, as long as that mass is close to the Earth's surface. And we found out in our lab that it was about 10 newtons of force for every kilogram of mass. So the gravitational force is 800 newtons in size. So it tells us how big it is. It doesn't tell us what direction it's in. Well, we know that the gravitational force is towards the center of the Earth. And our convention for direction when we're talking about vertical forces is that down is negative and up is positive. And so we'd say that the gravitational force is negative 800 newtons in size. And since the normal force is up, we'd say that the normal force is positive 800 newtons in size. So knowing this relationship between an object's mass and the size of the weight, the gravitational force of attraction on it, is going to allow us to quantify a lot of different force diagrams. Well, it gets a little bit more complicated when we have forces at an angle. This was our third example we talked about with a gymnast, let's say, hanging on some rings. And the ropes attached to the rings were pulling with a force of tension up and to the right and up and to the left on this gymnast. And so if we wanted to figure out how big, let's say, the vertical component of the tension was, let's say tension number 1, how much of tension 1 is pulling up and how much of tension is pulling to the right, if we knew how big the force of tension really was, let's say it was 150 newtons in size, the question is, how could we figure out how much of that tension is pulling up and how much of that tension is pulling to the right? What's the y component of the tension? And what's the x component of the tension? Well, we'd also have to know something like an angle. Let's say that this tension was pulling 30 degrees above the horizontal. Well, if we do that, remember this is a right triangle where the actual component of tension is the hypotenuse and the y component of tension in this case is opposite the 30 degrees. And the x component of tension is adjacent to the 30 degrees, we've got a right triangle. We can just use math that we know works for right triangles. So just a quick little review. If we have a right triangle, which means one of the angles inside of that triangle is 90 degrees, The longest side is called the hypotenuse. And if we know one of the angles, the side that's opposite the angle, in this case here, is called the opposite side. And the other side that's next to the angle that's not the hypotenuse is called the adjacent side. And if this is the case, there's actually 4 equations that we can use to figure out the length of unknown sides of this right triangle. So we have that the sine of the angle is equal to the length of the opposite side divided by the length of the hypotenuse, or the cosine of an angle is equal to the length of the adjacent side divided by the length of the hypotenuse, or the tangent of theta is equal to the length of the opposite side divided by the adjacent side, or we get the Pythagorean theorem. Normally it's a squared plus b squared equals c squared, or in this context, we've got o squared plus a squared equals h squared. Essentially, I want you guys to think about these as equations. The sine equation has 3 variables, theta, opposite side, and hypotenuse. And we can solve for any one of these 3 variables as long as we know the other 2. And the same thing is true for the tangent equation, the cosine equation, or the Pythagorean theorem. So let's do that for this last example with the gymnast, just to look at one example together. So let's say we have the hypotenuse, which is 150 newtons, and we want to figure out the length of the adjacent side, or the x component of tension, or how big the y component of tension is. So we know the angle, that's theta, 30 degrees, and we know h, that's the hypotenuse, which is the actual size of the tension force, which is 150 newtons. So if we have h and we have theta, and we're looking for the x component of tension, well, that's the adjacent side, since we know this given 30 degrees right here. So we're looking for a, and we have h, and we have theta, so we're going to have to use the cosine equation. So plugging in what we know, we get this. The cosine of the angle, which is 30 degrees, is equal to the length of the adjacent side, which is the x component of tension. That's what we're looking for right here. And we have to divide by the length of the hypotenuse, which is the actual force of tension, 150 newtons. If we solve this for the x component of tension, we multiply each side by 150 newtons. We get that the force of tension in the x direction, or the x component of tension, is equal to 150 newtons times the cosine of 30 degrees. That turns out to be about 130 newtons in size. So the x component of this tension, how much of that 150 newtons is pulling just to the right, is about 130 newtons of force. If we look at the y component, that side right here, that's opposite the given angle. And so we're looking for O in one of these equations. And we have either A, the adjacent side, which we just found, or H, the hypotenuse. So we could use the sine equation, or we could use the tangent equation. Let's just use the sine equation. We're solving for O, which is the y component of tension, the length of the opposite side of a right triangle. We have H, and we have theta. And so the math is just this. The sine of the angle, the sine of 30 degrees, is equal to the opposite side, which is the y component of tension, divided by the hypotenuse. We do a little bit of algebra, and we find out that the y component of tension is just 75 newtons of force. And just before we go on, I just want to make sure that it makes sense. Our numbers seem to agree with our diagram. And when you look at this, if we have a 30-degree angle here, as long as you're drawing your right triangles fairly close to what the angles are, the relative length of the x component and the y component should help us figure out whether the values are close to correct. You can see that the x component should be larger than the y component because this is 30 degrees. And you can see numerically that the x component is definitely larger than the y component. That doesn't mean those are the right answers, but that's at least one way to check to make sure that you're moving in the right direction. Okay, the last example we're going to talk about is probably the hardest one, which is figuring out the quantitative forces for an object on an incline or ramp. So let's take the situation where there's a mountain biker who has let's say the mountain biker and the bike together have a combined mass of 100 kilograms. Let's say they're coasting down this incline at a constant velocity. So we know the sum of the forces in all directions are 0. Let's see if we can make a quantitative force diagram using everything that we know for this situation. Whenever you have an object on an incline, remember we want to rotate our coordinate system. We want to line up the x direction to be parallel with the surface or the ramp, and the y direction to be perpendicular to the surface. So we're going to transfer that over to make our force diagram. And we know that gravity is pulling down on the mass of the bike and the biker, and gravity always pulls straight down no matter what angle you're on, whether you're on flat ground or inclined ground. So there's a force of gravity pulling down the biker. We know that the ground is kind of getting flexed because the bike is getting pulled into it. And so it's going to be pushing back up perpendicular to the surface directly in the y direction. So there's a force normal on the biker by the surface. And if the biker is moving at a constant velocity, that must only be if there's a significant frictional force. And friction is always parallel with the surface. And so the biker is kind of going down the incline, so friction is going to be pushing back up the incline directly in a rotated x direction. So this is the qualitative representation for the force diagram. But again, remember, we want to figure out exactly how big the gravitational force is in newtons, exactly how big the normal force is in newtons, and exactly how big the frictional force is in newtons, assuming that the combined mass is 100 kilograms and the biker is moving at a constant velocity. So remember, whenever we have a force that's not in our x or y direction, whether that's the normal horizontal and vertical y directions or our rotated coordinate system, we want to find out how much that force is in the x or y direction. What's the component of gravity in our y direction, and what's the component of gravity in the x direction, right? So we can draw a little right triangle right here. And just to see like what's balanced, I'm going to make a little component force diagram. So we've got the normal force kind of pushing straight up in the y direction. We've got the component of gravity pulling in the y direction. That's the y component of the gravitational force. And we've got the x component of the gravitational force, how much of gravity is trying to pull the biker kind of down the ramp or parallel to the ramp. And if the biker is moving at a constant velocity, we know that the frictional force has to be the same size as the x component of gravity. And the normal force has to be the same size as not gravity itself, but just the y component of gravity. So if we can figure out how big the y component of gravity is, we automatically know how big the normal force is. And if we can figure out how big the x component of gravity is, we automatically know how big the frictional force is. Well, with a mass of 100 kilograms, we know that the force of gravity in the biker and the bike together is 1,000 newtons in size. And so we have the length of this hypotenuse right here, right? And so all we need to do is figure out how big this side of the right triangle is and this side of the right triangle is to figure out the y component of gravity and the x component of gravity. So the only thing we need to know is one of the angles in here. Actually, other than this one, we know this is a right angle. The x and y component are at 90 degrees to one another. So we either need to figure out this angle right here or this angle right here. Well, I'd have to give you one more piece of information, which let's say the angle that the ramp makes with the horizontal. So let's say there's a 20-degree angle here on our ramp. Let's try to figure out, are any angles inside of here 20 degrees, or what are the angles inside of this triangle? Well, to help us figure that out, I'm going to go back to the diagram, and I'm going to draw a vertical line representing the direction of the gravitational force, right? And if we do that, we've kind of made another right triangle where gravity is the vertical part right here. The surface, which is 20 degrees above the horizontal, is like this, and this is a 90-degree angle. So we have a right triangle, and if this is 20 degrees and this is 90 degrees, that means this angle up here has to be 70 degrees because the sum of all three angles of any right triangle has to be 180 degrees. If this is 90, that means these two have to add up to 90 degrees, right? So that means the gravitational force makes a 70-degree angle with the x direction. And notice we know that the x direction and the y direction are at right angle to one another. And if these two angles right here together are 90 degrees, if this part is 70, it means this little angle is just 20 degrees. So usually in these kind of problems, you're given this angle down here, the angle the ramp makes with the horizontal. And that angle will be the same as the angle that gravity makes with the y direction, right? And 90 minus that angle will be the angle gravity makes with the x direction. So let's move these things to our force diagrams, right? So gravity makes an angle of 20 degrees with the y direction, just like we found out down here. And that's true on this force diagram, and we can move it over here. So in our little right triangle, we needed to figure out one of these angles, and we found out that the angle that gravity makes with the y direction is 20 degrees. Knowing that, we can now figure out how big the y component of gravity is and how big the x component of gravity is. So we're just going to have to use one or two different trigonometric equations, our sine equation, our cosine equation, and or our tangent equation. So if we're trying to figure out the y component, notice in this case, this angle right here is 20 degrees. And if this is our known angle of 20 degrees, the y component is actually the adjacent side. And we know the hypotenuse, the real size of the gravitational force, which is 1,000 newtons. So if we're going to solve for the size of the y component of gravity, we're going to have to use the cosine equation. We're looking for a, we have the hypotenuse h, and we have the angle. And if we solve this for the adjacent side, which is the y component of gravity, we end up getting that is 940 newtons in size. So that means, well, and the y component of gravity is kind of in our negative y direction. So the y component of gravity is negative 940 newtons. And because the biker is moving at a constant velocity, we know that the sum of the forces in the y direction must be 0. So the normal force has to be 940 newtons in size. Now let's look at the x component of gravity. This is opposite our 20-degree angle. And so we're going to end up using the sine equation. We know the hypotenuse, again, is 1,000 newtons. Our angle is 20 degrees. And if we do the math, we find out that the x component of gravity is 342 newtons in size. So looking at our diagram, based on our rotated x direction, the x component of gravity is kind of in the negative x direction. So we'd say that it's negative 342 newtons in size. And the frictional force is in our positive x direction. And the sum of the forces, again, in the x direction has to be 0. Why? Because the biker is moving at a constant velocity. So the frictional force has to be positive 342 newtons in size. So now we have enough information to go back and quantify all the forces in our original force diagram. The biker is experiencing a gravitational force of 1,000 newtons, a frictional force of 342 newtons, and a normal force of 940 newtons. Lastly, I want to look at the force of gravity and how big the x component and y component is for different inclines. And let's assume that the mass of the biker, again, is 100 kilograms, so the gravitational force is 1,000 newtons. Well, how would you draw your right triangles differently for these three different situations? Well, remember, the first thing you need to do is figure out what the x and y directions are. And you always want to make sure that the x direction is parallel with the surface and the y direction is perpendicular. And so in these three situations, you're going to have to rotate the coordinate system more or less. We're again assuming that the gravitational force is 1,000 newtons. It doesn't matter what surface the biker's on, the Earth's gravitational pull, because they're in a gravitational field strength of 10 newtons per kilogram, is going to feel the same size force, in this case 1,000 newtons, because the combined mass is 100 kilograms. Before you draw your right triangles to see what they look like, we need to figure out where the angle of the ramp goes, the 10 degrees, the 35 degrees, and the 65 degrees. Remember, based on our previous conversation, the angle that the ramp makes with the horizontal, usually the angle that's given, that's the angle between the force of gravity and the y direction. In this case, the 35 degrees goes here, and we know this would then be 55 degrees. In our steeper situation, again, the 65 degrees has to go between the y direction of the gravitational force. And over here, in our not steep situation, that 10 degrees, again, it's the angle between the y direction, the rotated y direction, and our vertical force of gravity. So if we kind of make our right triangle, remember we're going to draw the y component in the y direction, and then we have to draw our x component, so the x component is in the same direction as our rotated x direction. Hardest part is drawing this little right triangle. Once you do it and identify not only the size of the force of gravity, which is the hypotenuse, and this little angle inside of here, you can just use sine and cosine to figure out how big the y component is and the x component is. Okay? On a shallow incline with a gravitational force of 1,000 newtons, there's only a little bit of it in the x direction, and most of that gravitational force is in the y direction. Okay? When it gets steeper, Notice the gravitational force isn't changing, but there's more of that force in the parallel direction, trying to speed up the biker down the inclined direction. And notice there's less of it kind of pulling the biker into the ramp, so therefore the normal force will also be smaller, pushing back out. And in the steepest situation, as you can imagine, the x component of gravity will be larger than the y component because the force of gravity, more of it is in the x direction or parallel to the surface than it is in the perpendicular direction. So I hope this video helped you think about how to quantify force diagrams, whether you have vertical or horizontal forces only, or forces with components, either x components or y components, or situations where there are objects on a ramp.